In this video tutorial, we will look at calculations involving thin lenses. Calculations involving thin lenses are very similar to those for curved mirrors. The equations are identical, and so are many of the sign conventions. The major difference is the presence of a negative focal point for concave lenses. If you recall, a concave lens, also known as a diverging lens, causes parallel light rays to diverge, moving away from each other. Because these light rays will never come in contact with each other, we must backtrack the refracted rays until they intersect at a virtual focal point. This is now our principal focus. Because these backtracked light rays are not real, neither is this focus point. As such, this area is considered to be virtual, and any distances we measure here must be negative to show the reader that it's a virtual distance. As such, the focal point here is also negative. With a converging lens, also known as a convex lens, parallel light rays are refracted and converge on a single point along the principal axis. Here is its principal focus. Because these light rays are real, this side of the lens is considered to be the real world, so any distances measured here have a positive value to tell the reader that it's located in the real world. This includes the focal point, and so this focus is going to have a positive value. But other than that, everything we do today on lens calculations will be similar or the same to what we did with our mirror calculations. So let's begin. A convex lens of a magnifying glass is held 2 centimeters above an ant. So this wording might be confusing for some students because they see the word above. And when we think about the word above, we think of height. But this is not saying that the height of the object, in this case the ant, is 2 centimeters. It's not 2 centimeters high. It's the distance between the lens and the ant itself that's 2 centimeters. So in this case, we say the distance of the object, in this case the ant, is 2 centimeters. So be careful with the wording and how you read these questions. Now, if the image produced by the lens is 3.6 centimeters away and virtual, what is the focal length of the magnifying glass? So if you recall, a magnifying glass enlarges the object, making the image bigger than it actually is. In order to do this, we have to backtrack the refracted rays. Since the light rays don't actually exist back here, they only exist here, this is the virtual world. As such, any distances involved here are going to be virtual as well. So when they say the image produced by the lens is 3.6 centimeters away, we have to say the distance of the image is negative 3.6 centimeters away because it's virtual. And if you look up here, image distance is negative if the image is virtual. So be careful, the question may not tell you at negative 3.60 explicitly, but because it says it's virtual, it's implied. So you have to know that virtual values are negative. This is a common mistake students will make, and your final answer will automatically be wrong. So please be careful. Now the focal length of a convex lens is still going to be on this side. So the focal distance for this situation is still going to be positive. Only the diverging lenses or the concave lenses have negative principal focuses. So now that we have all these values, let's figure out which equation we're going to use. Since I'm trying to find the focal length and this variable is not present in this equation, I must use this equation. Inserting our values, we get this equation. Now I'm going to convert these fractions into decimals. Just make sure that when you do so, keep as many decimal places as you can, because if you round too early, your final answer will have a huge error associated with it. Alright, so don't round during your calculations, only round the final answer. Adding these together, I get 0.222 repeating is equal to 1 over f. But I'm not looking for 1 over f, I'm trying to solve for f itself. So I'm going to flip the numerator with the denominator, giving me the reciprocal, but because it's an equal sign, I must do the same over here. So f is equal to 1 over 0.2222. When I punch this in my calculator, I get 4.5 centimeters. So my image is 4.5 centimeters away from the magnifying glass, and it's much larger and virtual than the actual object. And that matches our theory that we learned yesterday. Alright, so for your assignment, you're going to do every other question, and just like the mirror assignment, the answers are located on the second page over here. So the bolded questions, the even number questions, are the ones that you must submit to me, and I will mark them as your assignment. The ones that are not bolded, the ones that actually have answers, you do not have to submit to me. However, I do recommend you do them because the answers are here. It's always good to verify and check to make sure you understand the topic before you do a question that is worth marks. Alright, so make sure you are checking your answers to make sure you're doing it properly. Now, Again, I've bolded the questions that you do need to submit to me. They are the even numbered ones. Let's go on to another example. A convex lens has a focal length of 60 centimeters. Again, convex lenses, also known as converging lenses, will always have a positive focal point. So we can just leave it as 60 centimeters. Just be careful if the question says concave lens. Well, concave lenses have a negative focal length. Alright, so just watch and read carefully. It then goes on to say that a candle is placed 50 centimeters away from the lens. Since the candle is my object, I say distance of the object is 50 centimeters. Please remember that height of the object and distance of the object will always be positive because we always compare the image to the original object. So by convention, the object is always positive. It then asks what type of image is formed, so is it real or is it virtual, and how far is the image from the lens. So we're going to calculate what the distance of the image is. In order to determine if it's virtual or real, it depends on whether this is negative or positive. If the image distance is negative, that means it is in the virtual world. The light rays don't actually converge and meet here. So we're going to use the same equation, and when I plug the values in, I can rearrange the equation into this form. Again, I don't really like fractions, so I'm going to convert them into decimals. Try not to round your numbers until the end, so keep as many of these digits as you can. And I get negative 0.00333 repeating is equal to 1 over di. Once again, I'm not trying to solve for 1 over di, I'm trying to solve for its reciprocal, di. Once again, I'm going to flip the numerator and denominator on both sides in order to give you the reciprocal of each. 1 divided by negative 0.003333 repeating gives me about negative 300 centimeters. Since the distance is negative, my image is virtual. So again, try out the sample question, compare your answer, make sure you're doing the problem properly. Let's move on to the next one. A camera with a 200 millimeter lens, so that means the focal length is 200 millimeters. So I'll write down focal length, 200 millimeters, makes a real image of a bird on film. Now, old cameras used to use film back here, but digital cameras now have an image sensor instead. But the theory is still the same. Light rays from the object enter the camera lens, where they are refracted and converge on either the image sensor or the film, depending on whether you have a traditional camera or a digital camera. Because the light rays actually converge here, they actually exist here, we say this is a real image. So that's what it means when it says this camera makes a real image of a bird on film. The question goes on to say that the film is located 201 millimeters behind the lens. So the distance from the lens to the image is 201 millimeters. Therefore, di is 201 millimeters. You'll notice it's a positive value because this image is real. The question then wants me to find what is the distance from the lens to the bird. So how far is it from the lens to the object? So we're trying to solve for DO. I think you know what to do at this point. We're going to use this equation, substitute in. I'm going to rearrange the equation to this, and then I'm going to convert these fractions into decimals. From there, I get 2.4875 and a bunch of other decimals that I'm going to keep is equal to 1 over dou. Obviously, I'm not trying to solve for 1 over dou, so let's solve for the reciprocal, and we get 40,200 millimeters. So that's about 40.2 meters away. And that, of course, matches my answer. All right, let's try another one. All right, so an object is 8.5 centimeters high. So height of the object is 8.5 centimeters, and it is placed 28 centimeters away from a converging lens. So the distance of the object is 28 centimeters. If the focal length of the lens is 12 centimeters, calculate the distance of the image and the height of the image. Let's start off with this one. So I'm going to look for the distance of the image. So again, I'm going to use this equation. Substituting the values in, rearrange the equation, convert it to decimals, and I end up with 0.047619. As always, I'm not trying to solve for 1 over di, I'm trying to solve for di itself. So solving for the reciprocal, I get 21 centimeters as the distance of my image. Now, in order to calculate the height of the image, I'm going to use this equation. But you'll notice the question did not mention anything about magnification. So I'm only going to use this half of the equation. Now I'm going to substitute the values that I do have into this equation. So height of the object is 8.5 centimeters. Distance of the image we calculate is 21 centimeters, but remember it's negative di, so negative of this value. And the distance of the object was 28 centimeters. Rearranging the equation, we get this, and when I solve, we have a negative 6.4 centimeters as our image height. Because the image is a negative height, that tells me that it is inverted and it's facing the opposite direction as my original object. Alright, so once again, only the bolded questions are to be done and submitted as an assignment. The other ones you should be doing as practice to make sure that you're on the right track.